Let's take a look at the energy density of a magnetic field in a solenoid. So we're going to look at this particular circuit right here. I have some sort of DC power supply with an inductor and a bulb. And the formula for inductance is based upon the physical configuration of the coils we have right here. So this lowercase l here is the length of the coils from end to end. Use of knot, permeability, free space. I'm assuming it's basically nothing inside there. Capital N is the number of coils, and A is the cross-sectional area. And there's another video, Introduction to Inductance, where I derive this. And also the magnetic field inside an ideal solenoid, U naught N over I, that is where the length of it is significantly larger than the radius of the coils. And that's not radius of the wires, it's radius of the coil. And so I derive that one in the magnetic field in the center of an ideal solenoid, and in another video where I look at a less than ideal solenoid and then just sort of check it by looking at the ideal case. So if we somehow short-circuited the battery, so we added in, and it'd be helpful if I had a red pen. So if somehow we bypass the power supply here, so in essence, what is going to happen to the bulb? Well, it's not going to go out immediately. It is not instantaneous because this is going to slow down the drop, which is the purpose of a solenoid. So that's the situation that at which we are going to look. And as I just talked about, it would not go out instantly. The inductor would slow down the change in the current. Again, that is the purpose of the inductor. So the energy, normally if I ask where's the energy coming from to light up the bulb, it's coming from the power supply. But if I bypass the power supply and short circuit that, then where's it come from? Well, it has to come from the inductor. So the rate of energy used by the bulb has to be the rate of energy provided by the inductor. So what we're going to do is figure out how much energy is the inductor, and we're going to realize that is the same as for the bulb. Now, using the lowercase convention for the time-dependent power and voltage and currents, so we'd still have the relationship of power is current times voltage. And if I look specifically at the inductor, the power of the inductor is the current of the inductor times the voltage of the inductor across the inductor. I know that the voltage across the inductor is equal to negative L or di dt, where L is the inductance. And just rearranging this a little bit, we get that. And so we end up with the power from the inductor, dt, is equal to negative L I sub L times di sub L. Integrating, I'm going to take the power from 0 to time, and then I'm going to take my current from whatever my initial current was, which I'm using as a capital I, down to 0 because we're losing, basically the current's dropping off. I know that power is the change in the rate at which energy is used with respect to time, and so the integral from 0 to t of PL dt is this ultimately ends up being the integral dE. E is the energy from 0 to E. And so the energy that is stored in the inductor is now down to this piece right here. And integrating, we get 1/2 I sub L squared from I to 0. Plugging in, we end up with 1/2 Li squared. That is the energy stored in the inductor, and therefore that is the energy that is fed to the bulb. Since that is stored energy, it is potential energy, so I have a formula here for the potential energy of an inductor, 1/2 Li squared. That also has to be the energy that is fed into the bulb, and so the energy from the bulb that is used by the bulb, 1/2 Li squared, where big L here, this L, is equal to the inductance based upon the configuration of the inductor. I know that the magnetic field is equal to mu naught little n times I, and we can express little n in terms of the number of coils per unit length, and so we can come up with a formula for the current based upon the magnetic field. We can plug that in for I, we can plug this in for L, so that's L, and this is I squared. Just doing some math, squaring what we have in here, and then canceling out common factors, we end up with b squared little l a over 2 mu sum naught. L is the length of the solenoid, A is the cross-sectional area, and so L times A, this piece right here, is just the volume. And so if I divide by the volume, because again, this is u sub b, if I divide by the volume, I get u sub b over the v for volume, and that's going to be equal to b squared over 2 mu sub naught, which is the energy density of the magnetic field. Now we applied this to an ideal solenoid, but it actually works more generally. And that's it.